Okay, all right. So good. So this class will continue with storage. In particular, we'll look at storage in context of economics problems. Basically, last time we looked at a bunch of constraints in a storage. So this time we'll try to put some numbers, right? If you want to maximize, let's say the profit you can get from storage, or you minimize the cost, how we use the storage. Okay, so that's for the rest of the class. So we'll look at sort of very simplified economic models. Right? We'll look at very simplified economic models, try to put some numbers to how big a storage should be, what are the different types of costs. Okay? So to recap, storage, last time, basically, we talked about a bunch of different technologies. And we talked about different sort of ways, different chemistries, different technologies of storage, right? So lithium ion, for example, lithium metal, flow batteries, fuel cells, all this different kinds of storage. So that's on the technology front. So now we're going to start to look at different applications. Okay, so instead of technology, let's look at what do you want the storage to do? What does it do? Right? So now let's look at applications. So what is one application for storage? What do you want your storage to do? Okay. Right, so you want to smooth it out, but why do that? So that's not a goal in itself, right? A smoother, okay, but then so you don't get money by smoothing out the market, right? So you don't get paid to say, "Oh, I made your market more smooth." That's not right. That's not what you get money for. So, why would you want to pay money, let's say, to buy a storage? Right. So one is come from basically reduce cost, or equivalently increase profit. Okay, so we're not going to buy storage just because we can buy storage. We'll say if I put in a storage, how much cheaper is the system? How much cheaper our power, right? And if you're a storage owner, you say if I put in storage, I can make money out of this. Otherwise, I wouldn't. Doesn't make sense putting storage. So this is one to make money. What is the other big application? There's two applications. The first one essentially, let's say make profit from a storage perspective. What is the other big application? So this is actually not the main application. So most storage today we have in the system is not really making much money. So we don't. Sorry? So that same thing here, right? So I put in here because the market pays something to do compensation, right? So still we don't really do compensation through storage. Okay. Yeah, arbitrage falls into this, right? I want to make some money out of it. Right, so backup is the other big application, right? So sometimes you buy storage for backup. So your hope is you never use it, but you still want to use it for in case you need to use it, we will use backup. So a very good example of where we have backup for storage. So let's look at backup. It's a bit easier to think about this application. So where are the most backup batteries? We actually have a lot of backup batteries. Where are they located? There's a lot in the Seattle area if you look at battery that just for backup. So which industry really wants to back up their power infrastructure? Right, so data centers, cloud computing. Basically, this is by far the biggest user of storage. If you look at storage capacity in the, let's say in the US, a lot of it is actually in data centers. That's where the backup capacities are. Okay, so computing is mostly uses this. Okay, because for, let's say, this is basically any cloud services. So there's Amazon, Microsoft, Google, all this, whoever that's computing. Because your number one priority is to be online, right? Provide service to people. Okay, so if power cuts out, you really need to still do computing. So you need to backup. And this is backup mostly, the first layer of backup is still storage. Okay, so this is sometimes sort of people don't realize how much storage we actually have in the system. Mostly these are in data centers. Okay, so most of these storage capacities are in data centers. Every data center now we build, you build a huge amount of batteries in the data center itself. Okay, but
normally these tests we don't use like one whole shutdown period, right? We just want to make sure that our diesel generator are 100%.
right, yes. So we'll talk about that. We'll talk about sort of how much battery you need. And think about, it's actually interesting to think about the layout and think about how you should back up this kind of thing in data center. So this is used a lot more than say utilities for building backup. Most buildings are still not backed up by storage, where data centers are all backed up. Okay, so for storage, we think about it. So we said last time, think storage is a box with a bunch of parameters attached to it. Okay, so let's think of, we have, so storage has energy and power rating. Right? Energy and power ratings. Okay, so if I buy a storage, you ask how big of a storage do you want? And how fast do you think it should output power? That's the question I'm asking. So this is in terms of, let's say, kilowatt hour. This is in terms of kilowatt. So how much stuff do I have? How much alpha? What is my alpha can be? So let's say if you're a data center, how big do you want your power rating to be? I try to size of storage. So let's say you're Amazon, you're running your AWS services, you have a data center, you need some backup, so you buy a battery. How big is your battery? How big? Like it's so big, but
Depends on the amount of servers.
right.
So the more servers you have, the more power. That's when I want to make sure that all servers are online.
Right. So the power rating is your peak load, basically. Right. So the bigger the data center, the higher the power rating you have to have. Okay. So this power rating, or a lot of times in sort of literature, is called power capacity. Okay, so I have a data center, I have some peak load measured in terms of electric power consumption. Okay, so let's say sending an email internally takes this much power. I process that many emails, so I have a peak load. So I need my power rating to be roughly peak load. Because if the outside power fails, and I happen to be at my peak load, I want to pick up all of this. I want to pick up all my peak load. So any idea guys have an idea how large this is? So I say for a reasonably large data set, how much power does so in Redmond, Microsoft has a data center. That's fairly large urban data center. And how large is the data center? Any guesses? So this is typically in the megawatt range. So megawatt to tens of megawatts range. So these are not small buildings. Okay, so a data center is, so again, our campus is about 50 megawatts. So 10 megawatt data center is 1/5 of our campus. Now our campus is pretty big. Like we have a lot of power consumption on the campus. So data centers are big things. Okay, so you buy a huge battery. At least a battery has a huge power capacity. Right, so what about energy capacity? What is this? Right? So energy capacity means how much energy do I have, right? So I have a very large power capability. But that doesn't mean I need to store a lot of energy. Right? I can have a huge power capacity with very little energy. So how long do you think this battery has to go? No, you cannot buy a 10 megawatt battery that runs 8 hours. That's the size of a lake. You have to. So this is typically about 5 to 10 minutes. Okay, so you have a battery that's very, very large power capacity, but not so large of energy capacity. It's quite a, or sometimes you use specialized batteries for this. So this is 5 to 10 minutes of operations. Right, so the reason you only need 5 to 10 minutes is this is a failover to conventional. So they have some conventional generation on site. Diesel is one good example. There are other ways to do this generation. Well, if the power cuts out, you run this, right? So let's say for 10 minutes, your diesel generator can kick on again, and then you operate, from your conventional generation. You don't have to operate from a battery anymore. Okay? So there's a particular types of backup for batteries for data centers. Right. So the next is it's interesting to think about. So next is think about if you have a data center, where would you put the battery? Okay, so what this battery looks like for traditional data centers is you have power coming in. So this is sort of grid coming in. You have a UPS. Right? So this is your battery, basically a power supply, uninterrupted power supply. Once the grid comes in, so this charges the battery. The battery sits within this UPS. This is your battery sits in this UPS. This goes to the rest of the data center. Okay, so this is the sort of the traditional data center battery design, right? So it makes sense. From a data center perspective, so it doesn't matter which of these is on. Right? So if the power cuts out, the UPS immediately turns on the battery and the thing runs. Okay, so this is a very easy design. Okay. So we don't build data centers like this anymore, actually. Yeah, there's why. So this is not a current design anymore. Right now, we don't build like this anymore. So this kind of building data center has an issue. No, big is okay. Like money is not terribly important for this. Okay. Right. So this has a single point of failure. Essentially, a single point of failure is this UPS. Right? So this because it's a big battery. This is a complicated UPS. There's a lot of high power switching going on here. That tends to burn out your UPS. If this goes, the entire system. Okay, so a lot of times failure doesn't come from the grid fails. The UPS fails. So for this kind of setup, more often than not, the data center goes out of power, not because the grid loses power. Your UPS has a problem in one of the circuits, then you lost power. So this is not a very good design because this is so-called, right? So you have a very clear single target failure, but be very careful with this UPS. Right? You have to do services, you have to maintain this. So this is not good design. So any alternative designs for this? Okay. Right. So basically, the alternative design is you break up one big UPS into many small UPSs. So but it's not that simple. It's not that simple because what this is. So the alternatives are more modern design, I guess. What more modern design of this looks like is you have power coming in. Okay, so this is your grid. This gets bunched up into a bunch of UPSs. Let's say UPS 1, UPS 2, UPS 3. This. Each connected to a server or racks of servers. Right? So this is a rack. Okay, so this is sort of more modern layout. As you divide a huge data center into smaller data centers, right? They have rows of racks anyways. So let's put each UPS here. Okay. This is still not the best design. Because here you still have single point of failure. For example, this thing goes, I lose a whole rack. I lose all my service jobs, right, which is not ideal. So how do I improve the redundancy of this? Right, so one is have all the UPS with all the racks. The wiring becomes very, very complicated if you have that, right? So a lot of racks, a lot of UPSs. So you cannot have all-to-all connection. That's too hard. So what you want is you want a connection. Right? You do want UPS to power multiple racks, but maybe not all. Okay, so what we typically do is this: we have an n+1 redundancy. N-1. So in power, in data center terms called n-1 redundancy. In power system literature is called n-1 security. So they mean exactly the same thing. So people who have taken power, this is exactly the same thing as n-1 secure. What this thing is just stay fully operational after a failure of any single element or single device. Okay, so that's what this is saying. I don't require everything to be able to connect to everything. Okay, what I require is if one of these things goes wrong, I can still maintain full operational capability. Okay, so this is called so in their literature again, it's called n+1. In our literature in power system, called n-1 security. It's the same thing. Right? You take one of them out, it should always work. So for example, if you have so let's say you have 3 UPS. So you have load, right? So this is, let's say, standard connection. So let's say this is a typical layout of, this is sort of a close to realistic layout inside the system. And saying that I don't have to connect to every one of them, but in this case, you can take out any of the UPS. I'm still backup, right? I still have backup, okay? So this is called architecture layout. This is called architecture layout. Any questions for this layout? So this is sort of close to, so for example, if you work for the electric engineering team or the power infrastructure team for Microsoft, a lot of your job will be designing this kind of layout. So you go to a huge warehouse, you look at what layout do I want, where do I put wires, and build this kind of thing. Okay, so this is for active team in Microsoft trying to build this. And the interesting with storage comes in this, right? So these are still purely aspect. So right now, current strategy is you always keep this storage as charged to full. Okay, you keep them charged to full. And if something happens, you just use the storage. Right? So you size the storage such that this guy can always power the full load here. This guy can power the full load here. This guy can power the full load here. Okay? So current strategy is you charge them to full. Okay, so currently this is what we always keep charging them. We just to make it as full as possible and make it stay there. So any drawbacks from this strategy? Many, many little storages in the system. Just keep them, at 100% capacity all the time. So there are some. Right, so one drawback is if you have a battery that's full all the time, it's not very good for the life of battery. The battery tends to degrade, so we talk about degradation mechanism. Battery tends to degrade when they're very full, when they're very close to 100% capacity. Right, again, if you have newer computers, will try very hard not to charge your battery all the time, right? Tries very hard to ask you to not charge it and keep it around say 70–80% full. So the drawback is not good for degradation. So they tend to degrade very quickly if they're always 100% full. And then you can say, well, maybe I don't need this to be 100% full. I make them 50% full. But then you need a bigger battery. So that's more costly, right? So you want a 100% battery to be 50% full, you just buy a bigger battery. Bigger battery costs more and doesn't scale linearly, so it scales exponential. And so it scales in a nonlinear shape. Okay, so what today now, so the current, so I guess so the newer generation, what people are trying to do is to do dynamic load balancing. Because I don't need to always assume these racks operate at full power. That's very, very rare for a data center to operate completely at full power. It's much more common, for example, this racks operate at 50% power, this thing at 70% so on. So what I need to do is I still need to make sure this thing is N+1 redundant, but not at the full power. So I can dynamically size the amount of charge in each battery. I can do rebalancing across the batteries. I can look at the load I have, and as long as I make sure I'm secure, then it's okay. I don't need to always size for the worst case scenario. So currently, the strategy is the new, I guess, the future approach. People are thinking about it. The newer layouts. What's the right name? Newer. That's operations. To do dynamic. Based on load. Because if you look at how much load each load is consuming, you can try to size the battery, balance the charges, use the shape, for example, energy from one to the other, maintain them at the right state of charge based on the load. This is where a lot of work is trying to go. Right? They try to do this kind of sizing for batteries. So the idea of having a battery that backs up the worst case possibility, that's too expensive for today. It's either you need a battery that's too big, or you degrade your battery too quickly. There's a lot more dynamics going on here. And this is similarly, for example, we talk about utility scale batteries. And again, you want to shift the load. You want to take into account that load is variable. Right? So if you're going to buy a battery for this campus, you're not going to buy a battery for the full capacity of the campus, right? You're not going to buy a battery for the peak power. You're going to buy it at some limit such that you can shift sort of load between buildings. That's sort of the goal of buying this kind of batteries. Okay, so this is for backup. This is for backup, and this is actually very similar to the grid because these loads are essentially random. You don't know what people will do, right? People may search different things. People may, for example, people may be watching a video. This are essentially random. So a battery that has to serve random loads. Right? So this is what you have. And there's a bit easier than grid because you have some control of the load, right? So if you're Amazon, you can sort of send different loads to different places. It's not like the grid where the load is completely uncontrollable. You have no control of the load in the grid. Here you still have some control of the load. So you both do load balancing here, and then you do sort of power balancing here to get away with the least smallest battery. Your goal is can make the battery as small as possible to still maintain sort of operational security for this thing. Okay, so that's the work, for example, that goes in a lot of these IT companies. And this is actually growing, this role is growing quite a bit in all those companies. So a lot of people, at least from this department, instead of going to utilities, they're going to do this kind of work once they graduate. So that's where because sort of this cloud computing has become more and more important, sort of the teams are growing quite a bit in all this things, trying to lay this kind of things out. Okay, so it's quite power starting to cost a lot of money, so they're starting to try to reduce the cost of having batteries in the system. Okay, so this for backup. I will try in this week's homework, which probably come out tonight or early tomorrow morning, give you an example with numbers for this. I try to get to a place where we can do the homework. So I haven't quite got that figured out yet, but I'll try to give you a homework with sort of semi-realistic numbers. And you can see sort of how those batteries should help each other to do this kind of thing. Okay, so that's my goal for this. This backup, and so in the grid, so similar challenges. Because if we all each buy a battery to back our own homes, that's probably too costly. We may not have space or money to buy a battery. The idea is, okay, can we share a battery? And you turn this into a problem. You have to sort of dynamic look at how much power somebody want, size the battery in the right way, and figure out a sharing mechanism for this sort of backup system. Okay, so backup right now has gone from just buy the batteries for your own load to sharing a battery, which is still challenging, so somewhat challenging for sharing batteries. Okay, any questions about backup? About data center applications? Okay, good. So this is for backup. Now let's look at the other thing as for profit making. So we're gonna now look at it from yeah, go ahead. Yeah, sure. Right. 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 Yeah. So for the grid, that's a hard problem. Because in grid, you cannot, like, whose power do you cut? Right? That's a question that nobody can answer. So we either have all blackout or nobody gets blackout. So in the utility, it's very hard to answer. In the data center, that's a considerably easier problem because you have control on your load. Right? There are some applications in the data center you have to do right away. For example, video streaming, right? Zoom calls. That has to be in real time. You have to process it. You cannot delay. Sending emails, it's sort of okay, right? Within few seconds, you can tolerate that delay. It doesn't have to go 3 seconds. Something like archiving, a lot of archiving going on in the data centers, or you have web crawlers that crawl different webs. Those can be delayed for days. It doesn't have to happen right? So they can have a lot of delays. You can ship it to some other data center. In a data center, there's ways to deal with this because you have controlling load. So by controlling load, the same time you're balancing power here, you can get things to pretty much match up. With the challenge that the load you delay, you have to eventually serve. So you're kicking down the line, yeah, and you hope sort of things works out for you, but it's easier problem here. So when in the grid is much harder. Like, what if we all want power? Then what happens? Like, who do you drop? Right? We're not very good at answering those kind of questions. Where for this it's easier. Okay?
So I think in the data center, you want to make all of your processing power, like kind of between all the processing power. So it's the idea to just have more computing.
Data center typically has a lot more computing than you actually need. So no data center runs at well, I should say that. So Avalon's data center runs at about 80% capacity. They're by far the most aggressive in running their data centers. Google's data center will run around 50% capacity. The data center normally is not the processing power, it's you need to build a huge building to put in the computers. Computers are very cheap nowadays, so it doesn't matter how many racks you have. So you go buy a huge building, then you slowly put stuff there. or you just put a lot of racks once you have the building and you don't use all of them. So you don't run, you're pretty far away from 100% capacity for computing purposes. Right? And yeah, so you're pretty far away from capacity. You always have some capacity. And if one data center is full, you can balance load across different places. It just, if you have a lot of video streaming, which we now have, this becomes more challenging. Because everything has to be processed close to where things happen. And then you have a very quick turnaround for Zoom calls. Before it was all sort of emails, which is much easier to deal with. For example, Google has enough data center processing capacity. So how many times do you think, if you send one Gmail, how many copies and routing do you think you have in a data center? It's processed many, many times. So a Gmail, every email you send in Gmail is copied and processed 21 times. There are 7 copies on the data center closest to you. There are 7 copies on intermediate data center. There are 7 copies on a long-term archive center. Okay, so losing the email is very hard. Yes, right? So they have a lot of capacity to do this kind of thing. There's copy, there's sort of process, all this kind of thing gets done. Okay? Whereas streaming is hard. Streaming is not something you can do. So this depends on application. So this is a bit easier for data centers. Actually, a lot of, yeah, so a big industry where for power system people to find jobs is actually data center. So they're hiring a lot of people to solve this kind of problems. The easier problem to solve. Utility is much harder. Utility is you don't know. Like you don't know what they're using the power for. Like there may be something very essential, or somebody saying, "Oh, I want to play computer games. I'm run a processor. I'm going to run my computer at a very high speed." Now it takes 2 kilowatt of power to run a fancy for gaming computer. In emergency, maybe you can cut that, but you don't know. You just don't know what they're doing. Right? So that's much harder for utility for grid. So I work in both areas. Data center is definitely easier to deal with. This is very hard. Here, the stochastic nature is we don't quite know. Like if you don't meet it, if you don't meet 1% of the load, which 1% do you cut? Like who do you not give power to? This is hard, but that's what you do. Any other questions about this backup application? So if you work for City Light, for example, if you go to the battery or the sort of smart grid group in City Light, you think about this all the time. You try to have different, you send surveys to people. You try to look at each load in each area, figure out who's the fire station, who's the hospital, for this kind of things. Make sure you don't get caught. For residential areas, and you do a lot of sort of surveys and look who's the important load. Okay, so that's why a lot of monitoring goes on. Okay. Right. Any other questions about that? Okay, so yeah, so grid, for power system engineers, like the dream is I can control load. Like that'll make everybody's life much easier. We're far away from controlling any control on the load. Yeah, okay, so we're far away from that, but that's sort of the dream. So you guys taking process economics, I don't know if you talk about demand response, that's sort of a way to control load. But it turns out people are not very responsive to demand response programs. So anyways, that's sort of people are trying. Right? So you can control both sides much easier. So profit making, going to profit making, right? So for backups, you really don't make money out of it. Your data center, like your battery, is just some cost you have to have. Right? There's no money. You don't make money by having backups, but that's just a quality of service. So normally you don't put a dollar amount, right? You're not, or your dollar amount that you have is just minimizing cost. Okay, so another way to look at this is maximizing profit. And the whole idea is you move energy around in time. Okay, so you have a time and right. So the goal is if you have a difference in the prices, then you can move energy by moving energy in time. You can arbitrage across different prices. Right, so prices are not constant. Prices are not constant, right? You can arbitrage the price out of it. So for example, if you look at last time, we look at solar. Where's my price curve? Right, so this is your price. For example, this is a actual plot of price in San Francisco. What happens is this is a very low price, this is a very high price, right? So what you really want to do is you want to charge here and discharge here. You make money through the sort of gap in price. Okay, so that's what battery is trying to do. It's kind of make up this sort of can I make profit. You have a battery, if there's price difference, can I do this? So the challenge, of course. Okay, so then if the price is like that, the question is why don't we just all do that? Right? It's free money from battery. So the challenge is that this is random. Prices are not constant in time, which is completely true. Price is also random, like a stock market. You can't, it's very hard to time it correctly. Okay, so if your battery and you're charged at what you think is low price, if the price doesn't become high enough, essentially you lose money, right? Holding that energy. So this is random. So you're gonna see probability, for example, here. Okay, so probability is not only about, let's say, load being random. There's also, you can think of the prices being random. Think about how much power should I use if this price is right. Okay, so this is the idea. Okay, and this is sort of the here really the algorithms matter a lot. So once the price becomes random, then your algorithms of determining whether the price will go higher or lower start to matter a whole lot more for this. Right? So that's where the a lot of work is at, a lot of research is look at the price. Can I have algorithm that arbitrage is successful in time? Right. So this is our. So let's give an example of arbitraging when price is random. Okay, so to have so for a battery to make sense, right? I need to basically for battery to make sense, I need to have two time periods. I need to at least have two time periods. It doesn't make sense to talk about battery in a single time period. So I need at least two time periods. So I have or two time slots. I have two different times. So I say T1 and T2. Okay. I have a price. So think of the price of electricity as dollar per megawatt. Think of this as a possible prices here. Okay. So let's say this price, because they're random, again, if your price is fixed and no, it's a trivial problem to use a battery. Like it's a completely trivial problem. So it's not very interesting. So let's say you have a random prices. Okay, so let's say this is 1 with probability 1/2. And then say 5 with probability 1/2. Okay. So I don't know the prices, right? I have some battery that has some randomness in the price. Okay, so let me make this even simpler. Let me make this even simpler. So let's say this is 1 with let's say I get to observe. This is just 1. There's no probability. This is just a fixed price. Here, let's make the prices more interesting. Okay, let's say this is 0 with probability 1/2, and 3 with probability 1/2. Okay. So it could be, I think of, why might be 0. Maybe at the future, I have a lot of wind or solar that pushes the price to be 0. Or maybe I have no wind. So that price pushes the price to be much higher. Okay. So in this case, should you use your battery? Let's say I have a battery with 1 unit capacity. The battery should you use your battery? to say charge in the first period and discharge in the second period. So right now I'm sitting at the current, right? This is my present time. I can buy price power at price of $1 per megawatt. In the future, there's two possibilities. I don't know which possibility it will be. If you're working with a battery, would you want to buy this? Right, so here the idea is maybe yes, because on average, right, this is 1.5. So you think on average, maybe you can make some money out of it. Okay? So one idea is to say, so if does arbitrage, right? So does arbitrage means buy in the first period, sell in the second period. Let's look at what happens. Okay, so the profit, right? So there are two possibilities for the profit. You may have a negative one profit with probably 1/2 because you bought the power. The second half the period time is 0, right? So you have 0 price. So there may be that you have a -1, 1/2, or 2 with probability 1/2, right? So this is your potential. This is your potential. This may happen. This may happen. Okay. So whether this is worth it for you or not, depending whether you can take this -1 hit or not. Can you take? Do you have? Can you? Will you accept this -1? Okay. So this is the idea we have. Okay. Right. So if you're a battery, what typically happens is you cannot hold your power indefinitely. Okay. So again, the thing to remember, battery is not an ideal battery. Holding power, one, power will be drained away, right? Power drains away from battery anyways. Second, you have degradation and so on. So typically you don't hold it that long. You cannot start charge right now and wait for infinitely long. Eventually I'll have a higher price, right? I can make money. That's not how battery works. Again, batteries are not perfect boxes. Okay? So normally the way you model is actually, you make decision here, you probably have to do something on this end. You cannot hold it. So I hold it for a year. It will eventually be high. So I can do that. So that's not the way it works. Okay. So here what you have is you have this kind of probability. So this gives you average profit of 0.5. So you have a probability of losing $1 or losing 1 unit of money, probability of gaining 2. So the average profit is 0.5 with some standard deviation. Okay. So you're not guaranteed. So the idea is, the way you're going to think probabilistically is you cannot just look at this average profit. Okay, so average profit does not mean, right? So this average profit of 0.5, you may look at this positive number. This also has a possibility happening, right? And you can bias this kind of thing a lot. What typically happens is, another example is normally your profit, there's no guarantee you'll make positive money out of it. For example, you can create another example of average profit of 0.5, but maybe with much more downside here. Okay, so there's different things you can create. For example, you may be okay with -1 and 2, but you can think of this as -10, and let's say 11. This may be your profit, right? It could be -10, 11. Then you have to think about, do you really, want to do this or not? Okay, so these two have similar average, but not a similar standard deviation. Right? So this is much wider spread. The spread of this is much wider than the spread here. Okay, so that's why both the average and standard deviation matters. So the statistics really matters, not just the mean. Okay, right? So again, it's important to think of all the outcomes, right? Think of all for the, again, think of probabilistic outcomes instead of just looking at the average. So this is same average. There's larger standard deviation. Right? So typically you have some average, some standard deviation. You have to think about whether it's worth the risk of doing this. You have to think about whether it's worth the risk of doing this or not. So typically what you have for storage, you have this kind of risk profit trade-off. Okay? So you have something that's your profit, but this is your average. I say this is your average. This is the standard deviation on axis. So normally what you really want to do is you want a very high profit and very small standard deviation. Okay, this is not possible. Okay, you want to operate here, right? This is the best part of your curve you want to operate in. This is not possible. You cannot operate at this point. Right? What typically happens is as your profit goes up, your standard deviation goes up. There's a more larger the spread, you have a chance to make more money, but you're also more risky. And then sort of the curve goes down like this. Okay, so here is 0, 0, you do nothing. And the curve goes down like this. So what you have is you have this kind of curve. You have this kind of curve. What's up here, this is the feasible region. So anything above the curve is typically you think as possible. You can attain everything above the curve, right? And then anything below the curve is not possible. Okay, I cannot have, normally there's no strategy. There's a very high average profit and low standard deviation. If there was a strategy, people would have used it. Right? So that was how, the market would have figured that out and very quickly price that in. All right. Okay. So this is your trade-off. And your goal is basically to operate at this Pareto front. Okay, right? So this is called the Pareto optimal front because every point here is sort of, every point here is optimal in some sense. Right? It's either optimal in profit or optimal in for risk, standard deviation. So you want to operate on this front. And using a battery to arbitrage in time, you want to hit this front. So you want to figure out where do you want to be on this front and figure out which of these points you can accept. And so normally you have to sort of figure out where you want to be. Okay. So algorithm design is basically, can I get to this front? And then somebody has to pick a point to operate. Okay, so the way this thing is drawn is, again, you look at the future, random prices you can have, right? For each, for the random prices, you can make a decision, and you can look at your mean and your standard deviation, okay? And then you can sort of put a point here. And then by looking at the different scenarios, you can start to draw this region, and you can see whether it's acceptable for you to operate on this curve. Okay. Any questions for this? So in the homework, you get more numbers to do calculations like this. Right? So see, so there's different prices, how much mean, what's the mean, what's the standard deviation. If you have a battery that, or you have two periods, you can choose to charge at one, to charge at the other, combine both together, what's the mean, what's the standard deviation. That's all this kind of thing comes in. Okay. Right, so this is very close to, so can you forecast the price? A lot of people are working on price forecasting. The better you can forecast the price, of course, the lower the risk. Right, so the lower the risk. So forecasting the price is really not about making more profit. We have a pretty good idea of the mean of the price will be. That's normally we have. We know the average. We don't know the spread. So we have a very good idea of the average. So forecasting nowadays is really about reducing the spread, reducing the standard deviation, not improving how much better you can do against the mean. Forecasting the mean is very easy. You can write, a pretty simple algorithm to get the mean correctly. standard deviation is very hard to get. Okay? You can get the mean, not the standard deviation. Okay, so this is the idea of sort of with randomness in price, you can do arbitraging, okay, for storage. Okay? So now let's take a break. Then when we come back, we'll look at the market where the load is random. So here we'll be looking at where the price is random. So then we want to introduce storage where the load can be random. And then look at the sort of, basically do a little bit of economics. Look at how load impacts price. And if the load is random, how would that, how are these, basically how is this price generated? Right? Why do I have these numbers? It's because load are random. Okay, so let's take a break. Let's break until 9:35. Then we'll look at the economics. Some more economics.
Like another rough draft and whatever we figure out here with the city. Yeah, there's a little bit of noise, but it would be nice to have, so, yeah. if you want it. Okay, so, I'm gonna talk about all of that because he's just great. Yeah. And I'm gonna post that. There's also he said like it could be open book or open book and open notes. But there are a lot of people who have. So like.
Okay, all right. So let's continue to the market, right? So the market we want to do is we basically want a better understanding of why the price is random. Okay, so one way to think about random price is just to accept it's random, and then just forecast what the price will be. Another way is to think about what drives the price, right? What causes price to change up and down so quickly. So here next we're going to look at sort of the spot market. So we'll do a very, very simplified version. Think about demand and supply balance. Okay, so this will be demand. Demand supply balancing, right? So this is the idea we'll look at, right? So again, so that here is, so I got the slides from Kurjan, basically saying that idea you want to think about supply and price as using alpha as one example is, as I get more and more of the stuff, I value less of it. So the whole idea is I have more and more of something, I don't want it as gets to a point. Okay, so this is, I think, alpha example. Can people see this slide? Okay. And so this is, if you only have one apple, I'm willing to pay a very high price. As you give me more and more, eventually I don't want it. So I get to a certain point where I'm willing to pay less and less money for stuff you gave me. So this is called a decreasing marginal utility. Our marginal utility is the utility or the value I derive from a good decreases as the amount of the good you give to me. Okay, so at some point, so this means decreasing utility in the value, right, of goods, right? So as a consumer, basically, at some point, I'm not willing to pay because the amount of utility I derive is lower than the money I will pay. So I stop paying, and so that's where the consumers will start paying money for something. So this is called a demand curve. Okay, so this is called a demand curve. This relates to the price you're willing to pay for something and the quantity that you get. Okay, so we have nothing, you're willing to pay a high price. We have more and more of it, you're willing to pay a lower price. So this is used very commonly for things like food, for example. Right? So this is very used commonly for food. For electricity, this is also sort of roughly true. Right? You have no power, you're going to pay a very high amount of price for power. If at some point when you have to consume excess power, you want to be paid money. That's excess power. Right? So this is a decreasing curve. So the assumption we'll make for the demand curve is this is monotonic, so it's always decreasing, right? It's in the same direction. It doesn't go up and down. It doesn't do that. And this is decreasing. So it's both monotonic and decreasing curve. This is called the demand curve. So the way to write it, this is Q equals to D of pi. And this is just standard notation. Right? So this was standard in economics. Pi is a price. Q is a quantity. Okay, so this is, so the quantity is so this is given the price, how much things do you want to buy at this price? So this curve that's drawn, this demand curve, this is pi equals to the inverse of Q. Okay, so you can read the curve this way. So you can either read the curve as given the price, how much stuff you want, or given a quantity, how much you're willing to pay. Right? So you can read the curve both ways. Okay, so this characterizes people's willingness to pay or people's marginal utility. Okay. And so this is basically given price the amount of demand that the customer is willing to buy. So normally we assume there are some curve for all kind of goods. Right? You have a good, there's a demand curve for the good people. So so for this kind of curve, basically since it's always decreasing, so what you really look at is how sharp is the slope. What you really want is how sharp is the slope. Is it gentle gradual decline like this, or is it something that's very sharp? Okay. So look at these two cases. This is called elasticity because elasticity just means the slope of this curve. Okay. So which one do you think of these describes electricity or describes power? right? Power is the top and bottom one, because you have a certain amount you want, and you really want that amount, regardless sort of the price. You're unwilling to deviate very much away from the quantity you want. So this is almost vertical, meaning that I have a quantity and I sort of don't really worry about the price. Okay? So this is, so electricity certainly falls in this, or electric power certainly falls in this sort of category, right? This is very low elasticity. So what causes this to be very low? This is normally an essential good, right? This is called essential good. And the idea is there's no substitution. Okay, so no substitution means if I don't have power, there are no other things I can use to replace power. Right? So that's why my quantity is sort of fixed. I have a pretty narrow price range. Okay, and this can cause, for example, there's huge swings in price. So your question, the last example was, okay, maybe at one time unit, the price is $1 per megawatt. Next could be -20 or +100. How can it vary that much? That's because this thing is a straight line. Right? So if your quantity moves away a little bit, you have slightly more renewable, slightly less renewable. This price has a huge range. Right? The dynamic range of price is very, very large. Okay, so this causes sort of wild price swings in the power market. Okay? So this causes very large changes in price. Okay, this is a huge amount of change in price, whereas very small change in quantity. Okay, so you think about sort of other commodity markets, right? I think what's going on around the world, you talk about oil jumping 20%, wheat jumping 10%, things like this. For power prices, we go from 0 to $1,000 per megawatt. So you're jumping sort of orders of magnitude at a time. So that's sort of the variation of power prices compared to some other things. So there's a sort of easy, called easy substitution. There are sort of things you can replace the good by. Okay, so you're not very, so you're much more, you're less, I guess, or you don't have a fixed quantity. You have more range. Power is definitely one quantity, changing price. Okay, so that's what also you hope storage to do, right? To smooth out this a little bit, smooth out this for changing price. Okay, so elasticity, we can define elasticity in the following way. So there's definition, and this is a good number to know because a lot of proposals in the electric industry is trying to sort of make this thing smaller, reduce this number. So what this means is a change in quantity. Okay? So this is a change in quantity over a change in price. Okay, so this is saying given a small change in quantity, given a change in quantity, how sensitive this change in quantity compared to this change in price. The easier thing to write is this pi over q. So you can rearrange this becomes dq over d pi. So this thing is, if you change the price a little bit, how much does the quantity change? Weighted by this ratio, by this elasticity ratio. So you have a dollar per amount, right? So there's $1 per stuff. You have this number, that's called elasticity. Again, for us, for electricity, this is a very large number. For electricity, what happens, this derivative is huge. Okay, it's very small change in price. Right? So so you have this sort of large, or actually you have this low elasticity numbers. Okay, so that's a definition we'll use. Useful thing to know about electricity. And then, so that's the demand side. And then next we can look at the supply side. Next we can look at the supply side. So this is the cost of production. Okay, so this is called a variable cost, or this is called a variable cost of production, because it's also a function of the quantity versus price. So it's just, also you have relates the amount of things you can produce to the cost or to the price which you can produce them at. So this curve now is pointing sort of monotonically up. Okay, so this is the way we're going to think about this. So what this is saying is it takes you more money, it's more costly to produce more stuff. Okay, so it's incrementally more costly for you to produce more stuff, right? So this thing has to go up. So this is right, to produce sort of the next unit of good, right? So as you try to produce more and more, it becomes more and more costly. So this is certainly true for things like a conventional generator. Because as a conventional generator, sort of the more power you want to squeeze out of it, you have to shove in more fuel. You have to get more fuel into the generator. You have to run the generator harder. So this is called the cost of supply side. The good exception to this is, right, so the exception to this is, let's see, if you look at renewables, so what does the curve look like for renewables? What does the supply side curve look like for renewables? Right, basically it's 0 up until a point where it's infinity. That's what renewable is. It's 0 from, let's say you look at solar, I can generate 0 power to the solar irradiance I have on my panel. I cannot generate a single unit more after that, right? So it's 0 cost until a point, they have infinity drop. Okay, so renewable gives you a weird curve. Okay, so renewable have the very, very weird shapes and curves. It's 0, 0 up to some point, there is infinity up to that point. So this is, think of this as infinity. This is not possible to generate more stuff here. Okay. And so almost you never see in other contexts actually this kind of supply curves. It's very, very rare to see this type of supply curve because what other things is free and then impossible, specifically free and then impossible. So this is a interesting shape for renewables. This causes a lot of problems in economic analysis because one, this is not an increasing curve for most of the time, then it goes to infinity. Okay, so this is flat, then discontinuous. Okay, so if you do math, you don't like this kind of curve. It's not different. You don't like this kind of curve, but this is sort of the reality we have to deal with. And again, this is also why you have very large price swings in the system. Okay, so if your total load, for example, come on this side of the renewables, you have 0 cost essentially, right? Or even negative cost. If your total load comes to this side of the point, your cost is very, very high, okay? Because you just cannot squeeze more things out of this anymore. Okay. And this point, depending on nature, and this is where the weird part is. This is random. And where this thing breaks, this is essentially random. I don't know how much price for wind again. I don't know how much wind I'll have. So my curve looks like this with a random jump somewhere in the middle. Okay, this for random types of jumps in the middle. And this, right, so again, makes things challenging. So this is not a great curve to work with from the analysis point of view. It's not the best curve you can have. All right, so in the supply side, then what we have is, so think of this kind of curves in mind. Think of this kind of curves in mind. We can, sort of in more generic terms, look at the supply curve as a price of marginal cost versus quantity, right? Versus quantity, and this thing goes up. So this is called a supply curve. So you have Q equals to supply of price. So quantity equals to price equals to as inverse of Q. That's kind of as inverse of Q. Right. So again, renewables causes some issues for this because this curve is not invertible. There's no inverse to this curve. And so that's a problem with this modeling. But anyways, so to keep things standard, you can roughly think there'll be some price marginal sort of supply curve. You can think of there's some supply curve in the system. Okay. And the reason, so we can still think the system has sort of supply curve is again, renewable still is not the dominant form of energy production. So what we're doing is we're taking the traditional conventional generator supply curve, which does look like this. The traditional generator curve is you can squeeze more things out of the traditional generator if you want. If you really wanted to, you can squeeze things out of it, right? Or you can turn on more generators, right? So you have this kind of quantity versus increasing price. What renewable does is sort of add a little bit jumps to this kind of price. Okay, so what renewable is, if you have a system without renewable, you have a more flatter side, and the renewable looks like jumps. Okay, so to rough approximation, we can still think of this kind of curve with renewable. Okay, so if the system becomes entirely renewable, then this goes out the window. Right? You don't have inverses anymore. You can't do this math. But still, right now, what we have for renewable is we're changing a sort of more smooth curve. Maybe it's flatter for longer, right? Maybe renewable is zero cost. So the first R is very, very flat. Instead of going up this kind of thing, it sort of goes up like this. This is where renewables things. Okay, so it jumps, or it includes this jumps in the curve. And again, the fluctuation in price comes from this sort of vertical jump. If you happen to land very close to this jumping point, you again have a big change in price. This sort of drastic changes in price. So renewables. So renewables in sort of putting this kind of jumps into it. Okay. All right. So again, this is also a good reason why we don't use storage before renewable. There's not, so we have storage capability. We definitely have batteries. We have lead acid batteries for a very long time. Nobody thought to use that for arbitrage in electricity markets. It's because there's not much price difference. Okay, there's no big changes in price. So there's not much opportunity to arbitrage. You know exactly what the price will be tomorrow. You don't arbitrage. There's no opportunity. Opportunity from arbitrage comes from, can you time the jump correctly? Can you sort of position yourself correctly for this kind of jump? Okay, so you have higher risk, but then of course you have higher profit, and that's why you need uncertainty on this kind of very, very sharp demand curve for this kind of to make sense of time arbitrage renewable. Okay, so think of this kind of, so that's something to keep in mind. All right, so taking this two kind of curves, so how do you get a price out of supply curve and the demand curve? Well, the price, you get the price by basically looking at market equilibrium. Right, so the idea is you plot Q and pi on the same axis. You plot both the supply curve and the demand curve on the same axis. So demand curve will be monotonically decreasing. This is your demand curve. Your supply curve will be monotonically increasing. Okay, and your equilibrium is basically the price both parties will agree to pay as essentially where they intersect. So you're willing, right? So you're willing to sell at this price for this amount of quantity. I'm willing to pay at this price for this amount of quantity. So we intersect, and this is our equilibrium. Okay, so this is Q star. This is pi star. This is the point of equilibrium, the price quantity equilibrium. Okay, so that's how prices are determined basically in the electricity market, right? So this is actually what happens. So you want to calculate the price of power at a location. You ask all the generators to tell you what their supply curve is. So if you are a generator and you're in the market, you have to tell the market operator your supply curve. The market operator puts all the supply curves together into one big supply curve. You look at the demand or the demand curve, you cross them, you get a money out. You get a money out here. Okay, so that's how we compute all this kind of equilibrium. Right? So the reason why the Pacific Northwest have a very cheap electricity is our supply curve is very, very flat. Okay, so the Seattle, if you look at around Seattle, we have very flat supply curve at very low price because we're hydro. Okay, so we don't like we have so our supply curve is like very flat, and you look at where the load is. If you look at some places like so in the US where you use a lot of coal, for example, the Southeast, then you do have a very sort of this kind of more classical steep supply curve, and the price can change a bit more. Questions about this equilibrium? Okay, equilibrium. So in practice, of course, the market is infinitely more complicated than this, but this is the assumption we will make for the market. Okay, so this is the equilibrium, right? Again, I have willingness to sell, I have willingness to buy. And then this is called equilibrium because we'll both, if we negotiate, we'll just reach this point. Right? So if we start off here, that means I'm willing to pay more. The cost I'm willing to pay is more than the cost takes to produce. So I agree to buy more, you agree to produce more. So move to this equilibrium. If I'm here, well, I don't want to pay the money you're producing. So it takes you to produce goods. So you're not going to produce more, right? You want to produce less. I want to buy less, we'll go to this point. Okay, so this is a good equilibrium. So that's why this is called a market equilibrium point, as this is our will converge at this point. So this is equilibrium. Okay, good. So before doing all these calculations, and to make the numbers more interesting for different problems we can do is the example I gave in the earlier, in the sort of beginning of the class, I give a negative price, right? So why would the price ever be negative? We do see negative price a lot in the US. Like anytime you go to the price map, you see it's not uncommon to see negative prices. So from this theory, why would it ever be negative? Like what? Right. Right. So what prevents you from sort of turning down the generation? Why can't you just turn down the generation and not produce? Why would you pay people to take power instead of just not producing power? Sorry? Right. Right. So price can be negative. It's because for a lot of generators, it takes time to turn them off and on. Right. So the interesting fact we have is storage often, like for storage, the dream is you hit this negative prices to charge and make money both ways. That's really the dream for storage. It's where you go downhill both ways. You hit negative prices to charge and hit positive price to sell power. You make there, even if you don't sell it, if your power just sits in the storage and being drained away, you still make money. Okay, so that's a golden dream of storage. So one thing we can look at is negative prices. This is common. So every day you see some price in the US being negative. It's not a rare thing. Okay, so you see, for example, Midwest on windy days, you see sort of negative $10 per megawatt. Okay, it's getting paid to consume power. But whether it's good for it's probably not very good for the environment, right? It's being paid to consume power, but you do see this kind of prices in there. And the reason for negative prices to come in is because of sort of binary constraints. Okay, so normally if your constraints are continuous and convex and this kind of things, you don't see negative prices. And this doesn't happen. When you see this as binary constraints is sort of shutdown time. And so this, for example, is for nuclear. You cannot shut down a nuclear power plant in a short amount of time. Because a nuclear has to generate power for some time. So there, you rather pay people to take your power than to shut down your plant. Okay, or it's just not possible to shut down the plant. There's things like startup cost. Okay, startup cost means if you shut it down, next time you start up, there's a lot of cost there. So you rather stay on for like an hour and pay people than to shut down and start up again. So this is again a binary. So these are called binary constraints because these are 0, 1 constraints. You're either on or off. That's you're either on or off. Okay, these are binary constraints. And this is startup cost. This, for example, coal, gas takes a lot of money to start coal up, for example. Okay, so they don't start up that fast. And they'd rather pay people to stay online, stay connected to the grid. There is one more constraint that makes some generator be on the grid. Can you think of another constraint that says, even if the price of power is negative, it should stay in the system? Right, so dams, right. So this is sort of hydro dams or burning garbage is actually another big thing in the US. As you're burning garbage, you have to burn it. And that will generate power. And so that has to go somewhere. So you burn the garbage, you generate power, it goes somewhere. So that has to go to the there. So this is called a must on. Right? So it's called must on things, right? So this is the biggest example is actually garbage burn. Which is not a small fraction of power in some states. It's depending on where you are, it's a significant amount of power coming out of this. So this must on generation, it cannot turn off. You pay people again to take your power because you have to serve other purposes. There is one more that causes the price to go negative, where again, you must be on. There's one more.
This is just an idea, but like renewables that might get like money from the government for producing a certain amount every year, they don't want to like just disconnect.
Right.
Because they want to be able to get that like minimum production.
Right. So so that's not a binary constraint, but that's sort of other economic consideration. Right? You have renewable mandates, for example, in California. I have to produce 40% power from renewables. They have to produce, right? Have to produce. So that's normally incentives. So that's not a hard constraint for something like nuclear. Nuclear is really an engineering constraint. Incentive, this is financial incentive. So renewables are paid to generate. So if it's negative $10 per megawatt, it's okay. I'm getting paid from somewhere else. I should still generate power. And so this is a financial incentive. There's one more. There's one more engineering constraint. One more engineering.
Related to the ramp down, or ancillary services.
But ancillary service is closer. So another is stability. I need the thing to be there to provide stability. And we cover I need the grid to be stable. So when I kick it, it should be stable. I need some spinning mass. I need some inertia. I need something to provide stability. So some generators you cannot shut it. You're there because you provide stability service to the grid. So you have to be on no matter what the price is.
Okay, so stability purposes. Okay, so this is why. So renewables actually doesn't enter these three. Renewables typically don't have shutdown problems. They don't have startup costs. This is still relatively small in most places. So these would really come from conventional generators. And the stability is an interesting problem. Like, can renewables provide stability? It's still a question that people are thinking about. Okay, but these are the reasons why you could potentially have negative prices in the system. And they do happen, and the goal really is to time it correctly. The goal really is, can you time the negative for storage? You really want to charge at negative prices, because there, once you charge, you already made money. Okay, you don't have to sell it. It's a future, even if you can't find a good time to sell, it's okay. You make, but really the trick is, can you make money both ways for a storage to break even? Okay. So we'll stop here today in the class, but you get homework later. It's looking at a lot of this kind of random prices. So do a bunch of examples. You have storage, these are random prices. How much money can you make on average? What's the variance? Or change the technology to say you have different efficiency. How much money can you make? This kind of thing. Do this kind of evaluation. And if you have an algorithm and to time this very successfully, you can make a lot of money. But right now, for storage is like the stock market. Many people try, but we're not always successful at hitting the right prices. So the people are trying, but again, if you go work, for example, for a bank, a lot of our graduate students at least go work for banks and develop algorithms to time the market for storage, to do this kind of arbitrage. Okay, so you'll see some of these examples in the homework. Yeah, go ahead. Nuclear is relatively flat. Yeah, so once nuclear is on, it's always on. So nuclear is this word. Nuclear is also sometimes called mass run generation, because it's shut down a nuclear power plant, you need about a week to shut it down, do maintenance. And so once it's on, don't shut it down. It's very flat. Gas has sort of the most typical supply curve. Gas really looks like a straight line, but the slopes not go like that. So that's for gas. Gas and coal are those very typical.
So you mentioned that the stability it's renewable can cooperate to make the system more stable, or it's not the other way around, based on my understanding, because they are fluctuating, so they will impact the stability in a negative way, right?
Both are possible. Like, they definitely introduce more variations, right, into the system. So right now, we're trying to observe that we're using conventional generator. So that's why you hear us, we're making the system worse. But again, that's more of that's more of an engineering charge. Like, it's not they cannot provide stabilization, but they have, all renewables have some form of energy storage, right? So think of type 4. You have a type 4 synchronous machine, right? You could at least provide short-term stability. For solar panels, you have capacitors. You have all this storage, so you could provide short-term stability. The longer-term stability, maybe a storage can provide longer-term stability, right? So it's not that we have to have rotating machines, because we just haven't figured out all the engineering part. So that's, again, for us in this department, a lot of work is trying to tie the system together. Any other questions? Okay, good. So yeah, so look for a homework coming out tonight or tomorrow morning. That's our last homework we'll have for this class.